Okay, good evening, everybody. I'm sorry a little bit late. Um, okay, so let me firstly look at our schedule. Sorry, I just opened my voice and let's look at the course materials and the schedule. And good evening. Uh, Let me pull out the course information here. Uh, let me share. Uh, okay, hope everybody is here. You're almost there. Um, so let's look at where we are here. The last class, we are first time to introduce the linear time series model. Remember, we're talking about two parts. So one is linear time series model. Definitely, we will give a review today. And then we're gonna talk about what is autoregressive models, which is AER model, just introduced in terms of some basic statistic or mathematics properties. Okay. And so today we were gonna finish the AR part and tap into the MA model a little bit. Okay, so last class we still leave a very important topic of autoregressive models. The topic is that what is the criteria to cut off the past historical records? For example, we know that autoregressive model is basically xt is the function, which is we want to predict, is the function of xt minus 1, right? That means tomorrow's value, for example, like a stock market returns, we assume will be function of yesterday, right? So it's, or today, right? So there's only one variables. There could be two variables. That means tomorrow's stock returns could be both today's and yesterday's. That's going to be two level, order two. So the question that which day we want to cut off, right? For example, like past the 3 days or past the 4 days, what is the cutoff, the historical records we need to predict for the future? That's our task for today's class, right? So the AR model is our first time to introduce linear time series models, so we put a lot of time on that. Definitely the MA model is another type of linear time series models. So this two will be lay very important foundation for our forecastings, right? So if you talk about, for example, nowadays, right? Nowadays people talk about the big data, people talk about the forecasting, people talk about the machine learnings. So even sometimes talk about the deep learning. So what those functions is, the target is simple. We want to predict the future behavior, right? For the business, we want to predict the future consumer behavior, right? What kind of products you want to buy, right? We experience every day. And in the finance or economics, we're more likely want to forecasting the investment performance, right? Or some social observations, right? Populations, income, or whatever, things like that, right? So these are very popular and well applied in terms of the concepts, right? So that's the big background, and we were gonna also review a little bit today. That's probably the two chapters we were gonna focus on in those 2 weeks. Okay, that's the one thing. Another thing I want to mention is that I will give you assignment. Okay, the first assignment I would like to, and the first assignment is that is here. You want to go to your Blackboard and look at your also, okay, maybe you have not reached that far. Let me look at this. Uh, Content, someone. Okay, so let me share the screen for you. Okay, so this is the content of this class, the content, and I have put assignment one there, and you cannot observe right now because this might be my fault. I should make it available right now, but it'll be officially available tomorrow morning. Tomorrow morning, and so you will have a 1 week to answer that. Okay, so it'll be show up tomorrow morning, and let me open this for you. Okay. And so this is assignment one. Okay, assignment one. So it's give you 1 week to finish. And the first question will talk about how to calculate the simple returns and the log returns. You just simply use the example in your first class slides. And now the first class is a review, right? So I think the second class, the introduction of the financial time series data. I think we have a couple good examples how to calculate simple returns and the log return. Just follow their steps. Okay, so this is the one thing. The first question. The second question, just simply use the autoregressive models. Order one. That means I give you the equation. I want to forecasting, for example, the returns and based upon the yesterday returns. That's only order one, right? The lagged. So I give you these equations, and I want you to calculate what is the forecasted values, right? For example, if I tell you the 100, when t equals 100, the return is something numbers. I don't want to forecast what is the expected value when the t equals 101. That means 1 period ahead. I'm pretty sure it is also a straightforward question, and I will point out what some similar examples in this today's lectures for the AR models. Okay, those questions just simply use hand calculations, right? Pencil and paper, that's fine. And so the third question is we're gonna using a little bit R. So I will give you a data file, okay, a data file, a simple monthly simple returns of a CRS because you don't care about this, it's just a database, where does stock come from? The DICEL 1, 2, 4, 5, 9, 10, it's just simply I construct the several portfolios. You don't need to care about what the finance story behind it. Just simply know that there is going to be 1, 2, 3, 4, 5 column of data, different portfolios, different return, just simply numbers, right? So I give you the data, there's a time series, right? So I just want to work out for this column DICEL 2, DICEL 10, what's going to be the sample mean, standard deviation, skewness, medium. Again, so those command will be just only one line command. And I'm pretty sure we already have examples in the previous classes, right? Just follow their command. I say almost a copy and paste. So, but you need to understand what is standard deviation, right? What is the skewness, right? They will give you the answers. And the second one is testing the hypothesis that the first 12 likes of autocorrelation are zero at the 5% level. This one is just like the last class we discussed. I think we use the chi-square distribution. The chi-square characteristics will show up the p-value, right? You want to reject or not. When the row, the correlation equals 12, it is zero or not, right? Again, so I will gonna also talk about today's class, right? To re-emphasize that. So all in all, this is a assignment one, okay? So let me know if you have any questions. This give you the 1 week and the next March 11th to submit. You can, you want to put all of your, for example, hand calculations, right? And the codings, the R code and output in a one file, like a PDF, whatever you can upload to the Blackboard. Okay. Okay, tell me if you have any questions.
The submission of the assignment is gonna be on 11th by the night time, or in 11 in the morning time, or what the due time? Oh, 11:59.
That 59, right? Okay, so I want to make sure I clear that. Okay, so just going to be hand calculation. You can take a picture of that or you can write down in a Word file. I'm pretty sure those are just a couple of lines is enough. Okay, not simple. This one just give me the R output and the code. Okay, so or you can give me the computer screen snapshot is also fine. I'm pretty flexible on that. Okay, okay, so there's another key point. If you unluckily stuck onto some programming problem, okay, so for example, you spend a lot of time still cannot figure out, unfortunately, I can't help you during the assignment, but you can ask me other questions from the class materials, but I can't answer you for exactly this question, okay? But if you have really some coding questions exactly for these questions, you just hand over there, leave it there. Take the picture of the anything arrow report or something problem you can't go through. Just leave it there. Give me the screenshot. I will give you partial credits. Okay, if it were the case, but I hopefully you can solve by your problem because I'm pretty sure this is not a so hard questions. Very, I would say straightforward. Just follow the examples. Follow the examples. Okay. Okay, so you will tomorrow morning you will see that this file, the txt file, will be the data. Okay, you can see here the data is a date. This is a calendar date. This is the calendar date. This is a just different column. But in finance, we see there's a different portfolios. This is simply returns, different portfolio returns performance day by day in the past history. There's a lot of data, you can see that. So your first task will be simply read the data into the R environment, right? And then analyze simply. Or use the examples, right? What is the standard deviation? What is the skewness, right? Those statistical properties, right? Okay, so I hope this assignment one has been quite, yeah, go ahead.
uh, does we have to do we have to analyze the data or just the answers the question of the standard deviation and
Yeah, you just answer you will give me the R output file or coding file, right? So the R output will give you those values, right? In the R software environment,
oh, okay, just
right?
the screenshot of the R.
Yeah, in the R software, R studio, in the class. For example, let me give you examples, okay? Um, let me let you know what exactly examples could be. I think we have that, right? Let me open the lib1.r. Look at those files, okay? Let me open my R Studios. So this is the lib1 files we just presented before, and probably the largely highly possible that you were going to use the package fbasics, right? Read into the data will be, I would like to say, will be exactly the same like this, but you need to change your path to your own computers, right? For example, you want to examine what is the data looks like, right? Several lines, what the size of the data, right? And you might want to change the log return because this is the raw data is a simple returns, right? You might want to change the log return, but it depends on the question demand. If they didn't ask you to do that, you don't need to do that, right? And you want to plot that. I didn't ask you to plot those numbers, But I would like to say it will be a good habit. When you get some new data, you want to get some sense what the data looks like. So you want to plot them to get some feelings about that, right? So use the command. See, those are variance, skewness, mean. See how simple it is. It's unbelievably simple and straightforward. Just one word, that's it, right? So the second question is related to today's class, or last class actually, right? How to test there's a serial correlations, right? So I think the last class, but I'm gonna review a little bit on today's, right? In our environment. That's it, right? Okay, any questions? Okay, I hope you have been clear on that. And so let's go back to the AR models. Okay, the AR model talk about. So starting from the lectures, we just simply give you some examples what the AR model looks like, right? For example, I want to predict the US quarterly real GMP. And this model is obviously I use is order 3, cut off the log order 3, right? To predict what the futures, right? That's the things. So we can call them AR3. So in the next, we also give example what it looks like for order 1 AR model. The AR1 model is very important. The benchmark, we give a full-fledged the mathematical expression and statistical properties, right? Which I will gonna go over a little bit. And so the phi 0 and the phi 1 is constant. You want to estimate, all right? There is an interesting problem, okay? So although I was gonna discuss the estimation, remember at the beginning of the class or at your undergraduate level classes, for the linear regressions, how do we estimate these two coefficients? That means this number and these numbers. How do we do that? Do you still remember? The last class we mentioned that. We use the least square, right? That means we assume this is a straight lines, right? A straight lines. So a linear relationship. So we just make sure there's two coefficients that the distance or deviation from the real data points and the points predicted on this line minimize the distance. We call them least square, right? However, for the time series data, there's some interesting difficulties. The reason is that the data is correlated. For example, remember in the linear regressions, right? We have some assumptions. The assumption is that there should be no covariance, or I would like to say more strictly speaking, correlation should be zero between what? Between the X and the Y, remember? So for example, when I want to, for example, based on the income to predict your food expense, and usually, this data sample should be uncorrelated to each other's. However, look at this time series models. RT and RT minus 1, there might be. Okay, so there's some challenge over there. We can't use traditional, the least square. So we'll discuss more details. I just want to mention here, bring the question up front to give you some feeling that how interesting and a challenge a little bit for the time series regression and the model establishment, right? Okay, so we call this phi 0 and phi 1 as parameters, okay? And if we can get some values for both of them, they are called estimates, right? Estimates. So for example, this 2, after some as definitely the R studio will give you the solutions, what the 2 coefficients, right? Firstly, we want to explore the stationarities. The stationarity is very important things, right? Remember the graph. The last class we also show like an Apple stock, the stock returns. It's relatively stationary. That means although it looks like a very volatile and a chaos, but the value is always fluctuate around 0. I mean, the return, not the stock price, but the returns is almost around 0, right? Even there's a volatilities, but there's upper and the lower band very clearly, right? So in this case, we call them stationary. And reflecting from this model, what we can say, we say, okay, find one, the absolute value less than 1. Okay, so in this case, and the next, let's look at the mean, the expected values, right? How do we calculate that? We just simply take the expectation on both sides. The expectation on here, expectation on here, right? And this arrow goes to zeros, right? So we know that expectation for RT and the previous period, there should be the same. The expectation are same, right? So in this case, we can solve the expectation, right? Simply use solve the simple equations that, right? I still use the phi 0 and phi 1, right? Look at this. This is GMP, the quarterly growth rate. It looks like a pretty stationary, right? When I say stationary, that you can see that, right? Remember the stationary, how do we define stationarity? I think in the file, you can go to this file, the linear_ts.pdf. This file has some introduction, right? How to define stationarity. That means the first moment and the second moment, they are finite, right? They're finite. I mean, they're limited numbers, time independent, right? So for example, look at the expected value. It's around 0.01, around these numbers, right? How about the volatilities? Okay, the upper band is here, the lower band is here. Again, so this is still well defined. So that means maximum and minimum volatilities as well as expected values, they are quite well defined on their threshold, right? So there's kind of stationarity. Okay, so here, these figures, last class we also examined in the R Studio, right? Those figures, for example, the first one is examining what is the raw data looks like on the time series, right? Sometimes you can use your naked eyes to look at if it is stationary or not. This one is using the, you can see this, a 2 to 176 and a 1 to 175. So it looks like 1 day lagged. That I want to look at the 1 day lagged data if they're correlated. Looks like the trend is kind of in this direction if you regression line. So there's to some extent they're correlated, right? And this one is look at the 2 days lag data. You can see that the data points is more scattered around, right? And you can imagine that if I look at the 5 days lag, 10 days lag, the trend will be more and more unclear, right? So it's less trending. So that means there's no clear relationship. And if you look at this data, this figure is very important figures. It's very important figure. I would like to enlarge a little bit. So this figure talk about autocorrelations. That's the new words we mentioned that. Autocorrelation, it just in time series, it just simply means the correlation between the past periods numbers, right? The stock return like the yesterday and the day before yesterday and the last week. We just see if there's some lagged correlations there. So look at this. When lag equals 1, that means what? That means it is itself, right? Today, stock returns 0 lag, it is itself. It's just simply today's. Of course, the correlation is 100%, right? So it's gonna be 1 here, see? And then when the lag equals 1, that means today's stock returns and yesterday's, there might be some correlated, right? So you can say it's here. The blue dotted line here represents the confidential interval for the significance. If the vertical line is break the dotted blue line, that means it's significant. If it's within the scope, that means insignificant. It's normal than zeros, right? And you can see the lag 3, sorry, lag 2 days lag, they're still correlated. That means today's and the 2 days before correlated. But beyond that, there's no correlation, right? So I would like to say for the US quarterly growth on the GMP, the correlation will be stopped at like around two quarters, right? That's it. Let me know if you have any questions when I review them a little bit. Okay, so this is unemployment rate, right? And obviously you can see there's some seasonalities. There's some seasonal, right? It's always like a spike, follow up, falling down, a spike falling down, a spike falling down. So there's some seasonalities we can expect that. And can we say the unemployment rate is stationary? Well, let's talk about the intuition. Do you think unemployment rate will be increasing or decreasing indefinitely as time passed by? That means the unemployment rate will increase continuously. In that case, we call them unstationary. No, the unemployment rate cannot be increased infinitely, right? So it just should be up and down, up and down, up and down, around like 2 or 3%, 6%, 7%, whatever. It cannot be increased forever or decreased forever. So in this case, intuition tells us unemployment rate should be stationary to some extent, right? On average, like 4% or 5%, something like that. Okay, so now let's examine the property 4, Now sometimes if I replace like using the expectation of RT equals mu, I can reimpress the AR1 model like this. There's nothing much meaningful here, it just looks like very clear, right? This one represents the time periods T, the performance against expectation. You can see the deviation. This is the previous period's deviation, their relationship, right? That's it. And we can calculate the variance, right? The variance. So the variance, I think we're not so required here, right? There's no deviation, so it's not necessarily required, but I think we have it later on, right? You just simply remember that this is the variance. Okay, and you can see here, coincidentally, the phi1 square should be less than 1, or this number become negative, and we know that the variance could never be negative. It's always positive. So in this case, again, the phi1 square should be less than 1. So it's consistent with our definition before about the stationarity conditions, right? And the autocorrelation, let's define the one lag correlation is a phi1, right? Sorry, the rho 1, and it should be exactly same as a phi1. Phi1, remember, it's a coefficients, right? And the 2 time periods lag is phi1 square, right? And you can see that the longer the times lag, the correlation should be decrease a lot, because remember the phi1 is less than 1, right? When you take the square, it will be smaller and smaller, right? So again, so the k periods lag behind will be phi1 to the k power, right? So it's going to be decays. Now let's talk about the forecast, right? So remember the forecast is related to the assignment 1, right? So my assignment 1. So for example, so let's say the model is like a xt phi1 xt minus 1 plus at. Let's assume the phi 0 is 0, like that. It doesn't matter, right? If I tell you phi 0 equals 5 or point, whatever number, just substitute into that, right? Just assume there's a model.
Sorry, Professor.
No problem. Yeah,
I have a question. Just if you can go back to when you, with autocorrelation, the P, which I think you referred to as foo, not phi, that's the lag. The P, like the autocorrelation under 6. Yeah.
Yes.
I know. Yeah. So the P1 or foo, I think you said? That's what you said it was called, right?
Oh, it doesn't matter. Just a Greek letter. It's
Oh.
a row one. P1, fine. It's row, the
Okay,
Greek letter.
but
Yes.
that's
It should be
the
exact.
lag you said?
It represents the correlation one lag behind.
Correlation 1 lag behind.
Yeah,
Okay,
that
and then the
means
next is correlation 2 lags behind.
correct. Okay, correct.
Okay, I just wanted to get that. Okay,
Yeah,
thank
no
you.
problem. No problem. So this is a phi one. Okay, phi one is exactly the equation. Remember, go back to, it could be easily lost. Let's follow. This is phi ones here, coefficients here. Okay, so this is only for AR1 model. So we summarize properties here, just show that the nicely closed form solution for some statistical properties. But for the longer period lags, the AR like 5 or 6, we have to use computer software, right? But so far, AR1 is more than enough to demonstrate some mathematical background. And sometimes it's very intuitive, actually, very intuitive like this, right? Autocorrelation will be decayed exponentially as the lag increases, right? Again, so let's go back to the key part here, which is related to assignment 1. How to make a forecasting. This, I think, this is just no more than substitution. Using some high school mathematics is more than enough, right? For example, I want to look at the 1 step ahead forecast at time n, right? 1 step ahead. So we can write this xn 1 ahead, right? With the head here equals to phi 1 xn, right? Why can say so? That's simply because, remember, I just replaced t, right? N plus 1, just t replaced with n plus 1, xn plus 1 equals to xn plus 1 minus 1. It's just simply n, right? So plus, remember the arrow term. When you make a forecast, we assume the arrow goes to zeros. The arrow is a kind of a random shock. We can't predict it. So we always assume it's 0, right? So in this case, we can have such a closed form solutions. The 1 period ahead should be equals to phi 1. Just copy the coefficients xn here, right? So again, so this, you can think about this like xn plus 1. I just write down like this one. That means starting from xn point 1 period ahead is equivalent to say xn plus 1. They're the same thing, right? Equals phi 1 xn. Just follow this relationship closely, right? Because period ahead equals to like 1 period and the relationship, right? So in this case, you can, if you know what is the xn numbers, you know the phi 1, you can easily calculate what is the 1 period ahead forecastings, right? So this is one. Okay, so now the question is that there could be some errors, right? How do we compute errors? Remember, we have already calculated the forecasted value in the first step, right? And now if we know the next period values n plus 1, we can take a difference, and that number will be simply the arrows, right? So an plus 1 is unpredictable, right? So there's some interesting point here. Why n plus 1 arrows at the next period, the 1 period ahead, we can't predict. Why? Because it represents the shock at next period. For example, I want to forecasting tomorrow's stock market returns. Definitely the tomorrow's stock market return should most likely different from today's. Why there's different? Because there's some shock. Could be from the news medias, could be from the industry, could be from politics. But whatever it come from is so-called shock, right? Shock, and it's unpredictable and it is random. So in this case, it's unpredictable here. Okay. So again, this is another properties. So the variance, right? The variance sometimes, okay, so we know that arrow is unpredictable, is fine, but I want to know what is the variance, right? Well, what is the kind of magnitude of such uncertainties? So again, let's tell you the answer. The variance will be simply the standard deviation of a square, right? So some standard deviation a squared. That means this part, right? The standard deviations. That means the 1 period ahead variations will be simply equals to the arrow part variation. They are the same things, right? Okay, so just simply the 1 period ahead forecasting. Let's look at what the 2-step ahead. If I want to predict what's the after 2 days, for example, the stock return looks like, I can simply use that. Phi 1, take the square. That's easy, right? Just simply Phi 1 based on the 1 period ahead forecasting. So it's going to be Phi 1 to the square, right? Starting from today, right? It's n+2 forecasting, right? So the arrow, we can do the similar things for the arrow term. And now we can also tell you the solution that what is going to be the variance of the 2 days forecasting is going to be this. Okay. So, okay, so well, if you want to ask me what the usefulness of that, this is very useful. The reason is that if you want to differentiate with the graduate students and undergraduate students, if you want to differentiate a good, for example, data analyst and just just simple the data analysis or whatever that's the differences, right? You want to understand what is the mechanism or mathematical behind the softwares. That's the very important things, okay, for such a work, right? So okay, so this, I think we have summarized a lot for the this is for extension for the M periods ahead forecastings, and I think we didn't mention in our assignment so far, so you probably don't need to read much into that. Okay. And this is the interesting point, that the property 8, we want to sometimes write into a compact form. Remember the B, the capital B represents a 1 lag behind, right? 1 lag behind. So I can write down in this format. So RT minus, if you can develop this bracket. So BRT represents RT minus 1, right? Because B is an operators, which means 1 lag behind, right? So when you develop that, you can see this equation will be exactly the same as the AR1 models we mentioned before. We just write down in some compact form, right? Okay, but here is you don't need to locate that. This one is a little bit advanced. Okay, it's a little bit advanced. Now I just want to quickly to go over the AR2 models, because of a lot of properties is very similar to the AR1, but just simply extension on some format. Firstly, look at this format of this estimation models, right? We just simply add into another term. Entertain the model with the second orders cutoff, right? And we can write down in a compact form. Now you can see why the operator B is useful here. When you have a more lag behind items, I can write down in this format, right? Okay, so this is a kind of interesting 2 variables equation, something like that. We will mention that what is the usefulness of the items inside the bracket. We will mention that, okay? But now let's first talk about what is the mean. The mean will be simply this format, right? The format. So that means you need to make sure the phi 1 plus phi 2 altogether less than 1 to make it stationarities, right? And this is autocorrelations, right? And this is again, rho 0 or P0 whatever equals 1. That means it's correlated with itself, right? And this is 1 lag. That means if today's and yesterday's returns correlation will be like this. And if you want to take a more, when L larger or equal to, you'll be right in this format, right? This autocorrelate. We can calculate autocorrelations. Okay, so let's look into this. This one, I just simply want to mention briefly and not too much in depth, because I don't want to give you too many mathematics so far. Maybe already is more than enough for you. But I want to mention here is because it's a very important property related to the business cycle. We know that a lot of economic data looks like business cycle. For example, if you look the stock market returns, if you look the GDP growth rate, if you look the unemployment rate, we know that for those economic data, there could be all of a sudden a job or a change due to the economic recession, right? And after that, there is economic boom. When there's economic boom, then those economic performance will be bounced back. So you can imagine that those financial or economics data, they will behave in response to the business cycles, right? For such data. So coincidentally and interestingly, our model can capture this phenomenon, the business cycle. And it is closely related to this 5(1) squared plus 4(phi)2, right? If it is less than 0, it shows business cycle. And the business cycle, that means between each two boom and the two recessions, right? The length of the business cycle will be can be computed like this way, right? It just directly give you the formula. You don't need to look into why it's like this, okay? It can be computed like this way, okay? But again, so it is not required for you to understand, for example, like using some calculations by hand or prove. I don't need you to do that. Okay. Okay, so the simulation, you can neglect the simulation part here. You can press the cross sign here. It's a little bit advanced material, so we don't need a simulation. Maybe in the future we could. Okay, we could. Why the simulation is important, but I want to mention the usefulness for that. Okay, sometimes, for example, I want to look into the property of a group of data, right? A group of data, and however, we don't have those data. For example, I want to look into the property of AR1 models. We just mentioned that, right? AR1 model. However, in reality, we might don't have such data. No data behave like AR1 model, autoregressive with one order. So how can we research on the property of those data? I can generate a data, a fake data, and those data follows AR1 models, right? That is so-called simulation. I use the computer to generate a fake data, which is assumed to follow some equation or rules or models, and then we analyze their property. This is very important functions in the modern data analysis. We call them a simulation, but so far let's skip over that, or since we are just looking to the introduction part on that. And we will introduce the function with ARIMA, we will introduce later on. You don't need to worry about that. Okay. Okay, so again, so this is another advanced topic. If you have such mathematical background, you can read into that. If you don't have, that's fine, because this material is for a broad range of audience. For example, when we talk about AR2 models like this one, right? And we usually can write down in the matrix format, which is more compact, and we can operate in the matrix. But I don't expect you to do that, because it depends on if you have taken a mathematics course, so-called linear algebra. If you never learned that, that's fine. We can skip that. I think our knowledge so far is more than enough to operate in R Studio. That means for coding, for analysis, that's fine. Okay, but those matrix format is for more advanced understandings. Okay. Okay, so the next part is our today's focus. We want to talk about how to build an AR model. That's probably the question in your mind so far, right? We have introduced so much, but we want to know that if I give you a group of data, a raw data, right? Unemployment rate of, for example, if I give you a group of data, Australian unemployment rate in the past 2 decades, can you give me a model to estimate that? right? If I give you a group of GDP growth rate for China, can you use in time series to estimate that? So the time series model is interesting that no matter what the background, no matter what's the social format or the political system, right? If you give me a series of economic data, I can make forecasting. That's probably the most fascinating, the aspect for those time series data. Okay, so to build the AR models, I think the foremost important, I think we only needed one information to build the model. That means to what extent you want to cut off at the the period, right? You want AR1, AR2, AR3, or AR4. That's it, right? So that's it. So in this case, we need autocorrelation. We need autocorrelations, all right? And so the partial autocorrelation, you can see your text for the page 40. Page 40. Let me searching around a little bit if I have such a figures, okay? And then I will go back to the screen. And meanwhile, you can open your textbook and look the page 40 and that figure. Let me off a little bit and find that file. Okay, so see if I can find that. Okay. What is the partial autocorrelation? And we need the partial autocorrelation PACF to define what is the cutoff value for the lag periods to establish the AR models. Okay. Okay, luckily I found this. Okay, so let me share the screen with you. Okay, in your textbook you have such information, but you can, I think there's a different version of this textbook. Okay, you can Google online, but they're different format, but the materials are always similar. It should be here. So identifying AR models in practice. Okay, in your textbook you also have this page, right? Another in these chapters for the AR model, autoregressive models. Okay, so this part will tell you how do we find the cutoff for the order of the AR model stepwisely. Okay, so let me first introduce what is a partial autocorrelation function, and we use that concept to define what is the orders. Okay. For example, I have a regression model, right? RT equals RT minus 1. And I can add into RT minus 1, RT minus 2. And based on this order 2 AR2 model, we can add into RT minus 3, right? And I can add into RT minus 4. And those are just simply the coefficients we need to estimate, right? So what is the autocorrelations, partial autocorrelation? For example, if I want to know what's the time t, and the t minus 2, the two periods lag behind, their autocorrelation, they're called ACF. We can calculate ACF. The R can give to you, right? ACF. However, what is the PACF? PACF is so complex that we couldn't calculate by hand, but the computer will give you very fast and easy. Just again, so it's similar one-line command, right? One-line code. It's very simple. But the idea you need to understand. So that means the partial autocorrelation will try to measure the correlation between t and some like t minus 2 after excluding the impacts of t minus 1, right? So that means partial autocorrelation would simply matter the two different time periods, their correlation after deducting the impacts of those intermediary time periods, right? That's the so-called partial autocorrelations, right? That simply means that the coefficients will capture the partial autocorrelations. Okay, so that's the partial autocorrelation coefficients definitions, right? So what is the methodology or rationale to select the AR, to select the partial autocorrelation, to select the order of the AR model? So we have two methods, okay? So it's summarized here, I think. There's, let me see here. Yeah, there's two methods. Let me first introduce the first methods, okay? You can let the computer, the RStudio, generate a figure for the PACF, partial autocorrelation figure for you. Again, so it's very simple. It just simply means PACF. That's just simply copy the name. That'll be the name of that functions. Give you this, okay? It's very similar to the ACF, but remember it will be capture the pure correlation between two periods and after excluding the intermediary periods after including that, right? The partial autocorrelation. So it will give you these figures. Then we can pin down what is the time lag we want to keep in the models, right? For example, again, so this is a ARPACF, I think this is 0, 2, I think this is zeros. This is a 1, right? This is a 1. 1 and a 1. So the like 1 behind. So PACF is very significant. So definitely AR1 model, the order 1, we will keep that, right? And for the futures, it looks like the other orders is pretty much fit into the confidential interval of the significance. That means they're not beyond the dotted lines here. They're insignificant. So I think AR1 model is more than enough to be included, right? Because the PACF showed that it is significant, right? So the textbook give you some explanation here, how to read into the figure 2.6. Let me see if it here. For example, as another example, figure 2.6 shows that the PACF of the GMP growth rate, again, so we use the same data series. The two dotted lines of the plot denotes the approximate two standard error limits. So this sentence tells you that what's the meaning of this dotted lines. It represents the confidential interval of the significance, right? Confidential interval significance. And the plot suggests an AR3 model for the data because the first three lines of sample appear to be large. Okay, so you can see that's really subjectively to select, right? We have mentioned that like one behind, the partial autocorrelation is very large, right? It's understandable. But when I talk about my view, I assume we should delete this too, right? Although they're also very large, but it is not beyond the significance threshold. However, the textbook mentioned that we might want to include that, become AR3. So in reality, what you're going to do if I give you such work, right? But not this assignment, you're going to do this. You will let the computer, for example, for this case, it looks like, okay, you would like to try 1, 2, 3. The three, like the first leg is not so important, it becomes shorter and shorter. And in the future, even there's some significant in the future, you can disregard because it's too far away. So you can build a model for AR3, AR2, and AR1, right? Represents including the only like 1 behind, like 2 behind, like 3 behind, to see which model will give you the best performance. Usually we use R square, right? R square to measure that. Or you also need to look at the coefficients if it were significant or not, right? So all in all, they give you kind of a directions, save you a lot of time. Or if you don't have such information, you probably also want to try AR4, AR5, AR6, right? There's an unlimited version of that. So, but from this PACF, you basically say, okay, I want to limit my try to only maximum probably the 3 to test which model is the best, right? That is the one method. And we have another method called AIC and BIC information criteria. So these two criteria, although the textbook gives you some formula like this, right? But you don't need to understand what is the mathematical theory because we are not statistical, major or statistical master degree. We just understand the AIC, which is so-called information criteria. It's such a criteria to help us select which lag we want to include in the AR model. For example, like here. So the computer usually will generate AIC and BIC values for each lag, right? Let me write down what is information for you. So computer will give you for like 1 behind, like 2 behind, like 3 behind for each different version of model, right? This is the largest. The model can be complex so that 12 periods lag behind are included. So for each version, what is the AIC and BIC value corresponding to? And we just select the smallest, the minimum, okay, the minimum. Just look at those values very close. Like look at the AIC. Usually the AIC and the BIC will give you the same conclusion. They should be consistent. Okay, for example, like look at the AIC here. The AIC, look at those values, right? Look at those values, the two lines. Look at the AIC. So which lag give you the minimum, the smallest value? It is negative, remember. The smallest. Can you tell me, based on the observation, which lag, 1, 2, 3, 4, 5, 2, 12, which one give you the lowest AIC values?
6. Negative 5.847. I think that's the highest. No?
Thank you very much.
Yeah.
Yes. So I think this is good. Sorry, it's my bad. Let me see, it's the lowest or maximum. I think I forgot maybe. Let me say, I think this is a long time ago. So for example, the well-known one at the maximum. So.
I saw maximum
Oh, sorry.
there, but I don't see what it's also said. If you go up a little bit, it said maximum.
Oh yeah, look, the textbook mentioned that, the selection rules here. So you want to order K that has the minimum AIC values, and the same rule for the BIC. Okay, they give you the solutions, right? Just follow me on the textbook, like you can see here, right? Read into the paragraph. So they say for the 1 to 12 lakhs, the AIC value are close to each other. Yes, it's very close. It's around -5 point something, right? With a minimum 5.849 occur at p equals 9, suggesting that AR9 model is preferred by the criteria, right? So again, so you can use the AR9 models, right? And the BIC criteria, the minimum values at p equals 1 and p equals 3. So the BIC selects AR1 model, right? So that is a little bit, that's why I'm very uncomfortable with sometimes there's forecasting. That means even you have such a criteria, the conclusion could be diverse, could be, I mean, say not quite consistent. Remember when we use the PACF values, look at this curve. Remember we cut off like 1, 2, 3. There's a possible 3 type of model give you good results, right? But the AR1 give you probably the most significant. If you add into order 2 or 3, might be marginally increase the power of the model, might be. So 1, 2, 3. However, when you look at the if you use AIC criteria, the minimum at p equals 9, that means suggest the AR9 models. That means you just include t minus 9, right? The variable in the autoregression model. But when you use BIC, it reminds you like AR1 and 3 might be good candidates. So I would like to say, if you use the BIC criteria, it gives you the similar results with the partial autocorrelation criteria, right? The AR1 or AR3, but they are very different from the AIC criteria give to you, right? Remember the AIC and the BIC just find the minimum value corresponding to which order you want to cut off, right? So under this case, you may want to establish a model for all of the version, and luckily it is very, very straightforward. In the next, let's show what the results looks like. So, for example, I directly use the textbook to illustrate, but I think our PDF lecture materials is very same. So again, so they use different function name. You don't need to care about it because this is, I just randomly search Google, give me this materials. This book is so famous, so that's why there's a lot of elder version online. But the function is different, right? For example, they use a different software. Okay. So the first line is read into the data. You don't need to use them. You can use our own. Okay, but you can have such a command, for example, like AR, right? AR, and they will give you AIC information. Look, 1, 2, 3, 4, 5, 6, 7, right? 8, 9, 10. So there is a 12 group of value for the AIC, and then you just select which one, right? So you can see this is AIC. Okay, I'm sorry. This is starting from 0, always starting from 0. 0 means that there is no lag behind the item should be included, right? They give you the AIC, right? So this is 1, 0, 1, 2, 3. So lag 3 give you the minimum AIC. So you can define the order is 3 here, right? So again, so this part will just tell you how to select appropriate AR models, right? So just use the one thing is that you use the PACF graph to define which order you want to cut off, or you want to use the AIC or BIC criteria, and they will generate from the R software, right? So there's the two things that we want to mention here, right? Let's go back to the class materials. Okay, and
Wait,
there.
so sorry,
Yeah.
what command would we run on R to get the table to show us the AIC and BIC?
Yeah, no problem. We will introduce them next. Don't worry about that. It's very straightforward.
Okay.
No.
Sorry.
So far we just look into the criteria, right? So those are just simply the mathematical functions, and you don't need to care about how do we calculate this, right? Let's go back to the lectures. So in the R command, we have a clearly show that, right? Firstly, there's so-called AR because we want to estimate the AR models. We want to define what is the P orders, right? And RT here is simply the name of the data. You can name your own, right? I think this data read into the US GMP data. You can name whatever, right? This is a name by the lecture book. The masters equals to MRE. We will introduce more details later, but I just want to let you know what's the meaning of this. I just tell your computer, the R software, I want to use the MRE method to estimate the coefficients of the model. And of course, this part is probably the most difficult and important. We need the estimates of the two coefficients, right, for the AR models. And this name is so-called maximum likelihood estimation. And this method is different from least square we use for the traditional regression. This is another way called maximum likelihood estimation. So this method is actually more interesting. This method is such a method that will make each historical observation happens with largest likelihood, then the model will be successful. I want to select a coefficients of estimation of the coefficients such that the model give us the best estimation of the past historical data, the likelihood or chances it happens, right? So that's it. So it's called maximum likelihood. In the later on, we will give more definitions, okay? So order.max 12, that means you want to limit the searching of the order at the 12. Usually people don't want to even be, beyond that. Okay. However, let me give you an example why we want to limit the maximum to the 12. For example, in the stock market, for example, we know that everybody need to file the tax returns, all right, tax returns. And every year, like January, right, or February at least, as late as that, January. So when you report a tax, all of your financial returns will be taxable, right? Unlikely, there's things, for example, if you get some interest income, even $1, you need to subtract like a 30% of the tax, right? If you get a stock return, stock investment, dividend income, you need to tax. So in this case, if you look at this January's and the past years, there's always a big drop on the returns. We call them January effects because of the tax issues. So under this background, you will know that there's a correlation between 12 months because of the tax issue, last year and this year's returns. So you want to look into that in this situation, right? Okay, there's several points we want to look into, but which is very important, I think. First one, do you need a constant term? Check the sample means. Remember, for the AR1 model, we have two estimates. One is a phi0, which is a constant. The other is a phi1, which is the coefficients of the like item. So when in one situation, we will assume the phi0, the constant, existed. So you want to check the sample mean. That's very easy, right? Just look the mean of the data. If the mean is positive, and you may want to test if it is a significant or not using the t-statistics, right? So if there's some positive mean, then you want to include a constant term, right? For example, like a stock market returns. Usually some companies stock, the average mean is zeros, right? It's zero returns. So in that case, you can drop off the constant terms, right? Okay, so estimation, least square against the maximum likelihood. So far at our stage, we don't want to dig into too much into that, but you need to specify here in the computer to let the R estimate use MRE method. So after you estimate the model, no matter it's AR1, AR2, AR3, you want to know if the model is successful or not. So you want to examine several steps. One thing is that look at the residuals. right? The residuals. You want to make sure the residuals, there's no correlation. That means the residuals should be purely random. In statistics, we call them IID. That means independently and identically distributed, right? So that is also called white noise. In our class materials we mentioned in the last week, that's so-called white noise. That will be the perfect output of the residuals if the model is successful. So what you can do, you can simply plot a one step ahead forecast arrows, right, with the residuals. You just simply use the observation minus the fit, right? You can get the residuals, right? How can you get the residuals? Remember, the residuals is just arrows. Arrow is just simply your model predicted and the real data, right? It's the differences. And then luckily, the computer directly give to you. I think in last class we have mentioned that the residual is the one group of results reported in under the command for the estimation. The computer will directly give to you automatically. Okay, so it's here, right? Residual should be close to the white noise if the model is adequate, right? That means if the model is good enough, so it should be white noise, right? Okay, so the degree of freedom again is not required here. It's a required deeper understanding of statistics, so we skip that because it's not very much relevant for the coding environment in the software. Okay, so let's look here. I think the last class we have covered that, right? So just to go very quickly on that, what the data mean. I think most of the code we were going to use for the assignment 1. So let's look at which part is useful here. So this is just read into the file, right? Definitely you need to change. This is your own pass. You want to use the function fbasics. You want to read into the data. And then you want to look into which column you want. For this data, the first column is the data we want, right? Sometimes there's other information we don't need. So this so-called we want the data, the first column we want, right? And we want to plot the figure in the 2x2, all right, the organization. So the first one is to plot the correlation 1 day behind and 2 day behind. Last class we have demonstrated that in the last minutes, right? I think the code I also give to you the code on the Blackboard. You can download and run that, right? And it's just simply copied here. And so this is give you the autocorrelations, and this also give you the partial autocorrelation, right? Let's examine here. Let's go to the R environment, the last class where we are stopped. So here is the last class, right? So we use the the GMP data in 1982. So this is a data file should be available on your the computer. I also download from that. And so let's firstly run those 3 lines, right? Okay, we read into that and we draw the figures, right? The figures we have shown here, right? And the next is important, right? Next important. We want to draw the PACF because the PACF is the one that will give us the information which order we want, right? You can enlarge it, look at it, just click on the zoom here. So you can say it's kind of a first one, second, and a third. Looks like pretty much nearly close to the significance level. So the AR1, AR2, AR3 models will be probably possible candidates, right? And then we use the Box-Jenkins test. Okay, I just give you the hint. This command will be used for the assignment 1. Remember the second question of the second part, the question B for the last one. How do you test the correlation, autocorrelation equals 0 or not, right? So you can look at this, the box dot test, right? Lag equals 10. That means the maximum lag I want to check is 10 pairs lags, right? Let's run this. Okay, let's look at the report. The report is shows that box class, its p-value is, this is a very small, right? It's to the order of 10 to the -6. So it's very small numbers. That means it's very significant. So that means I see there is a autocorrelations, right? And so again, so this one, I just directly goes follow the command and explain that what's the meaning of this code, and then we'll go back to the lecture. Okay. Then here we just formally estimate the model, right? For example, this AR X. Remember, X is, how do we define X? X is the data, original data we name. You can name whatever you want. Okay. And method we use MLE, right? So let's run that. And it will directly give you, look at this results here, right? So it's gonna be show you that, and at this corner, right? It's gonna be show you 1, 2, 3 coefficients, right? Like 1, like 2, like 3 coefficients, right? Order 3. The computer directly give you order 3, right? So and remember the ML, this is the name of the handler. You can name by your own. You can use the whatever, Mike Johnson, your own name, whatever you want. This name just simply tell the computer that I will store all of the information generated from the autoregressive regression. There's a lot of regression. It's far beyond simply the estimation of the coefficients. And let me check what is inside. Okay, so that's why we use the names. So you can see there's a lot of information. There's order, all right, how many orders included, what is the series, what the frequency, what's the variance, mean, partial correlation, AIC, residue. There's a lot of information we're interested, right? So here, we just look into the residue, right? We want to look into if the residue is a white noise, right? If that means it's the more random, the more likely the certain white noise, my model is successfully established, right? So then we can plot that, right? Let's plot the residuals. Okay, so you can say the residuals looks like a white noise, right? It's pretty random. There's no clear like trending or you know, the or unstationary, right? It looks like very stationary and unpredictable. So I assume it's successful. So the next, based on your naked eyes, it's not enough. You want let the computer to test if there's autocorrelation on your residuals. So in this case, use Box-Jenkins test, right? Box test. Again, you can derive this. So the box test give you what? The p-value is 0.71. It's very large p-value, right? That means you can reject the null hypothesis that there's no correlations, right? So again, so our model is successful. So the next part, again, so we haven't finished the full task of is how to identify and establish the models, okay? I think our assignments actually is even simpler than these demonstrations. And there's alternative way we can establish model. Sometimes we use ARIMA model. So this is a full-fledged regression model. And probably I don't need to talk about here because when I in the next 2 weeks, when I introduce ARIMA models, I will introduce this format because ARIMA is just simply a combination of AR and MA. So there's an alternative way we can define the orders, just a different way to write about that. But there's nothing novel stuff here, right? Mathematically. So I just stop here, right? Okay, so let's go back to the lectures. Let's go back to lecture. Okay, so after examples, let's look at another examples. So another examples is that the monthly United States unemployment rate from January 1948 to 2017, right? So another data, right? For example, again, so this is a give you, I think that's data file. You don't need the data file because you can download this from a Federal Reserve St. Louis. They will give you the data. You need to, this package cont mode, right? Cont mode, you can use the require. The require just simply means the install. They're similar to install. You can use the require. That means recall that, right? The cont mode will directly link your computer to the Federal Reserve St. Louis, and they will give you the unemployment rate data, which is to the most recent. Okay. Let me introduce here a little bit. So this is the get symbols, right? On rate, because in the Federal Reserve St. Louis, there's a lot of data. We just need unemployment rate. So there's a so-called on rate, and this is source is a FRAD, the Federal Reserve. And a chart series. So this is simply directly give you what is the time series plot looks like. As that numerical, this is the interesting part, because the on rate here, this number, although it looks like a digital numbers, but they're probably not numerical. It might be some different object. Let me explain this a little bit. I might not give you such example in the class or assignment, but I want to help you to really enter into that. In our environment, this is a very advanced topic. For numbers, whatever the numbers, there could be different attributes. Sometimes the numbers is a class. For example, let's say number 1, 2, 3, right? 1, 2, 3. So the 1, 2, 3, it looks like a numerical number, but it is not numerical property. It is actually a class. What does it mean? For example, I say there is a 3 different group of people. High, medium, low. I label 1, 2, 3. So you can see in this case, 1, 2, 3 is not numerical property. It's just simply a class, right? Sometimes the XTS is a time series. Time series data is a special data in our environment. They will treat differently from traditional numbers. For example, if you give me a group of numbers like 0.1, 6.2, 0, 9, whatever, this totally looks like irregular. But if I tell you the computer, okay, this is a time series data, computer will immediately know that and it establish some relationship based on the time series attributes. So there's different attributes for the same group of data, right? So this function just simply adds the numerical, just neglect those special treatment or special attributes of data. Just simply force those data into simply numerical. That means, for example, 4.9, just simply 4.9. There's no other meanings, like a class, like a time series, no. It's just simply what exactly the number by itself means, okay? Now, so in this case, you can, this is a relatively high level function. You can try by your own self. If you don't have this function, see what's the results computer give to you. That will be a very interesting try, and it will make you familiar and leapfrog another, better for the R studios. Okay. Okay, so this is the data, right? This is the data. And here is another interesting line of a code you might be interested. It shows the TDXC 1830 divided by 12 plus 90 plus 1948. What is this? What's this? Can anybody tell me what's this from your observations? It's very hard, I think, right? This line just simply expresses the calendar time in numerical way. Remember, we have a treat this group of data not as time series. It's sometimes very good starting point because if the computer know it is a time series data, you need to follow the time series data analysis framework to do. It's a very sometimes problem. So we simply force those numbers to numerical type, just simply the number. However, if it were numerical type, those calendars will not be stored in a time series meaning. It just simply is number by itself. So you need to convert to the continuous numbers, right? So you can see this is kind of, I create a horizontal lines of the time, and it is from 1948. You can think about like a year, right? 1948. And 1 to 830, this is a total number of rows of data, how many days has passed, or I think this is how many months is, yeah, how many months is, right? You divide by 12, right? For example, if the 1948, the January, first month, that's gonna be 1 divided by 12. If the second month, 12, 2 divided by 12. So in this case, you can convert the calendar date to numerical number when you plot them. It will be looks like more friendly, right? So, and then you can plot that. You can use your computer to try this. I will not repeat here, okay? And then after you, those part, I think, which is so-called, it will be challenge. That means how do you handle with the raw data and to analyze them. In the next will be traditional, right? For example, use AR functions to calculate their orders, right? AR functions. And MLE and orders selected is 11s, right? It's 11. I'm not sure it's 11s, 2.1. Yeah, orders that's 11. I think they neglected some steps, right? Why they select the 11? I think they might need to show the PACF, the partial order correlation. I'm pretty sure there's the figures, okay? And then they will show order select is 11, okay? I think here is to select the 11 because 11 is give you the largest numbers, simply largest numbers here, right? 11 here, right? And then you estimate. Here they use the ARIMA, like I mentioned, that is the alternative way. You can directly use the AR models estimation at the previous examples, right? Okay, so and then directly similar, right? The ML, the stored information for all the regression results, right? Okay, so those things is not required. This is other tasks that we didn't mention in the class. We just simply skip that, right? Okay. There are some interesting functions. For example, like here, the predict function. The predict just simply means that I want to forecast. For example, like a predict I'm2 4, it just means that, remember, I'm2 is the name of the handler. I store or save the information for the regression. For example, there's a coefficients, there are residuals. The R is very convenient. You just simply write down the name I'm2. 4 means that I want to forecast the 4 periods ahead. Then they will give you the values. It's very convenient and very easy. Okay. In our assignment, remember the question 2. I want you to calculate what the 1 period ahead forecasting. That question I require you to do the hand calculation because I didn't give you any data. You just calculate using the mathematical the rules, which is mentioned in the textbook, right? Or class lecture materials. And again, so this now should be not very hard, right? It's just straightforward, simple calculations, right? Apply that. But in the later on, when we use our software, we have a raw data. We will use this ways. We use the predictive functions, and it lets the computer know how many periods ahead you want to estimate, right? A forecast, sorry. Right. Okay, so any questions so far? And if you don't, let's go to the MA models. I think we are lag behind a little bit in terms of the in terms of progress, but I think the MA model is, it's, if you understand the AR model very solid, in a solid manner, you should enter the moving average model, which is MA model, much easier, and as well as the future one, the AR MA model, because these are follow similar spirit. Okay, so moving average model, I think we probably have heard moving average before. Again, this is another parallel methods to estimate the forecasted time series data. I think if you remember, if you the pandemic, for example, the COVID, right? If you look at the COVID data for the New Jersey, they always report a moving average estimate, right? The moving average, and let me see. Let me introduce. Let me give examples. So for example, this is simply the New York Times Post, right? Which has simply searched the New Jersey, the COVIDs, right? The vertical spike every day is very irregular and very volatile. And the thick red colors, it is a moving average, right? It's moving average. And what you can find, you will find that moving average is smooth. It's much smoother than the each every days, right? This is a moving average, right? And if you look at the pin, if I stop at the pointer, you will see they explain this the thick red curve. It shows that 7-day average. 7-day average. So how do they compute that? That means, for example, this day's point will be simply the past previous 7 days average, right? Like this number is simply past 7 days average. This point is simply past the 7 days average. So each point on the thick right lines will be the previous 7 days average, right? And in that case, we call them moving average. So for example, if I want to forecast here, right? For example, like after 2 months, like this point, what's gonna be the good estimation? You definitely will assume moving average trend, this trend, okay? The thick red colors. And let me tell you the truth is that this curve is relatively hard for class, right? And because you can see the curve is very, I would like to say, it is very irregular compared to our GDP, compared to our or any unemployment rate, right? So I last month developed a method depends on the deep learning, the machine learning, artificial intelligence, and my methodologies can predict the moving average of the pandemic at a very exact shape. That means although it looks like irregular, but artificial intelligence like the deep learning can understand and read the data, make a really smart move on the next periods. So that's a more advanced topic in the future if you're interested. Okay, so again, that's why I see the moving average very very good power, and the two powerful tools to make a forecasting, right? That's it. So let's go back to the class. Okay. So we have introduced the intuition from the moving average, but mathematically, what is the model looks like? Okay, this model will be similar in this way. Let's look at the MA1 in the order 1 moving average model. So that's going to be the format will be the return, right? RT equals mu. Mu is kind of some constant, right? Again, we will examine the mean average of the data, see if there's such a mu existed or not. This is AT, right? This is AT. Remember what is that? It is a shock. It is unpredictable, and AT is the estimation between expected and the real data. And we can express the at time t, the return depends on the current shocks, of course, and the plus previous day's shock, AT minus 1, with some coefficients, hopefully less than 1. So what's the intuition behind that? It's also very interesting. For example, say the stock market, right? The stock market returns. The stock market returns today depends on their historical average, unconditional. This is the constant unconditional. That means independent of the time, right? Plus an AT. AT represents the shock received today, unpredictable. And plus the shock received yesterday. It's highly possible, right? For example, the yesterday, the information the stock market received definitely will impact today's performance, but the weight ratio will be decayed. And if you think about like, I can include like AT minus 2, AT minus 4. That means I include all the information shock in the previous days, but you need to assign a weight ratio, but because we're pretty sure the longer the fall behind, the information will be less influential on the future forecasting, right? So this is the intuition behind the moving average. So interestingly, right? So when you do the moving average curve like the pandemic, you actually unconsciously use this mathematical model, but I'm pretty sure you didn't realize that way, right? Because, okay, so let's talk about the stationarity. It is always stationary. You just remember that, always stationary. We will discuss why. Remember, for the AR model, we have some preconditions. Okay, so let's look at the mean value. The mean is very straightforward. You just simply take the expectation. Remember, for the shock, news shock, it goes to 0. So it's only mu here. It's simple, right? And if you look at the variance, all right, so you can do here is to give you directed solutions, right? 1 plus theta square, sigma square. Again, I assume no matter it's AT or AT minus 1, their variance are the same, which is the sigma A square, right? Like this. Okay, so you can derive a little, if you're interested, you can derive a little bit, right? How to get the variance of RT? You can get a simply variance of this 3 item, right? But remember, mu is the constant, so you can drop this. Remember, because when we value the variance, we don't need the constant. Constant does not impact, right? Because that means every data observation plus a constant is useless, right? It will not impact your variations, right? So you simply drop the mu. When you drop the mu, you just simply AT minus theta, AT minus 1 left, right? So it will be goes to this format, right? I just give you a hint on the direction if you really want to derive by your own selves, right? Auto covariance, again, so this is another properties. So covariance, one lag behind is going to be this, and the other than that case will be 0. Okay, it's an interesting case. It's very interesting. That means for the correlation covariance, it's only last for 1 day, RT minus 1 days. If it is say T minus 2, T minus 3, T minus 4, many days beyond that, the covariance will goes to zeros. That means under the moving average 1, MA1 model, we assume that. I think it's very self-explained. It's not so hard. If we assume that only 1 day lagged information does work, of course, beyond day 2, day 3, there's no impacts, 0, right? So that's why the covariance or correlation goes to 0 when the L larger than 1, right? And again, we can count the row 1. That means 1 day lag behind was their correlation. Again, they directly give you the solutions. So What's the property of autocorrelation? What the property of that? What the meaning for the real data? The real data means that under the MA1 models, don't remember what happens 2 time periods ago. It's a short memory data. It's not long run memory, short memories. Okay. So here, if I want to make a forecast, what it's going to be looks like it's a very similar, right? So if the one step behind is R as time Tn 1 period ahead equals to mu minus sit An, right? Remember, in this case, why we take this format, why the n plus 1 disappear? Because at time n, the information An is known, but An minus 1, that 1 period ahead information is not known. So we directly drop that. It's very similar to the forecast arrows. Forecast for the AR model is very similar on that. Okay. Okay. So the arrow, the 1 period ahead, my arrow will be n plus 1a, right? And multi-step ahead. So for arrow larger than ones, okay. It is not require you to derive, okay. It's not required to derive, but well, for me, it's no need to derive, right? Just look closely here. 1 period ahead forecasting mu minus An. But if it's 2 periods, 3 periods ahead forecasting, why we only have a mu left? Why there's no n plus 2, n plus 3, n plus 4? That is simply because remember for the moving average order 1 model, the periods beyond 2, there's no correlations, right? There's no correlation here. Right? That means information beyond 2 days lag will be useless. So in this case, when you're forecasting multiple step, right? Beyond 1, like 2, 3, 4 periods ahead, they're always constant. There is no more shocks anymore, right? But for 1 day ahead, it's still there. Right? It's still there. Right, that's a little difference for the moving average compared to the AR models. Right. Okay, so the multi-step were not required so far here. Now remember, because in our assignment 1, we are only tackle with AR forecasting. That means the purpose slides. This one is new stuff in today's class. Okay, maybe next time I might be question that. Okay, so invertibility, this one is not required because again, so this part you probably need to understand the linear algebra to understand what the meaning, but and it's a little bit deeper in the statistics. I think I better want to skip that. I don't want to mess up or the mind because we want to sometimes computer already do something for you right now nowadays. Okay, and the last directly goes to the 2 periods lag behind moving average model MA2. So in this case, it's just simply extend to AT minus 1, AT minus 2, and associate with weight ratio 6 theta 2. So you can also write down in a compact format like this, right? Again, stationarity, mu, variance like this, autocorrelation, rho 2 will not be equal to 0. That's also understandable because you include the 2 periods lag behind the information here. Definitely the correlation for 2 periods will not be 0 anymore, right? So, but if beyond the 2, the correlation will be equal to 0. Again, this is understandable because in your model, the beyond the 2, there's no information, useless. The information is useless, right? We only cut off here for the information shock. So again, similar thing. If you want to go forecast beyond the 2 periods is always equal to mean, the mu here, the mu, right? The mu here. Okay, so you can see where it goes relatively fast when it goes to the moving average model because they share the similar knowledge when we look at the autoregressive AR models here. So the next question is that how do we build a MA models, the moving average? Similar technique. Now we will look into the autocorrelation function curve, which is interesting the first time we introduced. Okay, now the PACF, ACF. Um, there's some reasons behind that, but if you really want to know that, we can discuss right in after class. But I would just say so far you don't need to require to understand that. But again, you just need to know the rules, right? How do we cut off the order, right? Which order for the MA model we use? We examine the autocorrelation functions. But it is still understandable and very intuitive, I think, right? Just all of a sudden, I just think about that way. Remember for the moving average models, for the remember for the MA2 model. So for MA1 models, let's say for MA1 models, the correlation when there's a like one, the correlation is some number. When there's beyond one is zeros, no correlation. That means the autocorrelation will be only some numbers for like one. Beyond one, the autocorrelation equals zero. Now let's MA2. For MA2, it's similar, right? Again, for the autocorrelation, if it's pure 2 will be not equal to 0, but beyond 2 will be 0. Okay, so what you can find, that means you can use the ACF autocorrelation to examine. When it is begin to 0, no more than 0, it will be cut off at that order. It's very straightforward, right? Okay, so we use the autocorrelation as the criteria, right? And so the estimation, again, so we use the maximum likelihood math. You don't need to know the details, it's beyond our scope here. Okay. Model checking, again, same, we want to make sure the residue versus a white noise. All right. And then forecast, and luckily the forecast, the computer can have a package forecast. You just specify how many periods you want to forecast, right? But usually for our class, I might give you in assignments that you want to hand calculation what the forecast 1 or 2 period we had. But remember, for the moving average model, we are relatively easy because if you're beyond the orders, if you're beyond that, I would like to say it will be the forecast what directly goes to the mean average, right? If you look at the properties. Okay, for model for R parameters will be like this, right? We want to estimate what theta 1 to the theta q here, right? These examples. Again, so we can use the another data, IBM data. I think we have the data on our file. Just you can find that by your own self. Examine the data, right? And then look at the ACF, check the ACF plot, right? Find out which is the cutoff, and then establish MA model, right? Here they use ARIMA, which is again the alternative versions. So I think I'd better want to move to the next class to talk about ARIMA in a more systematic way, because ARIMA model is kind of a synthesis of the MA and AR. Is kind of a comprehensive model, combines two formats to increase our forecasting capabilities. So in this case, R give you a very convenient way. You enter the ARIMA model, you can specify as MA, like here, that's 001. That means this is purely MA1 models. Okay, so this is MA1 model. You just express the model in a different format. So I think I want to combine this part with next week's class to discuss what is the meaning of ARIMA, and we will use in the future, we will all use the ARIMA command to establish AR model or MA models, right? But all in all, the MA model is very similar because we just use the autocorrelation to examine which order we want to stop. And the next step will be very similar. We just look to check the residuals, right? If the white noise, if there's no autocorrelation, right? And that's it. So we'll stop it that ways, right? Okay, I think this is pretty much closed for today's materials, and I want to leave some time, right? If you have any questions, you can discuss me, and if you have no questions, don't forget the homework will be show up tomorrow mornings, and you have a 1 week to answer that, right? And later on, you can put all of your hand calculations and the R output and the code in a one PDF format or whatever the Word, and upload on the Blackboard. That's it. Thank you. If you have no questions, you can leave the room. Thank you. Good night.